Hi everyone, New Redev here. In this program, I'm going to talk about beautiful but lost algorithms. It really means that there are a lot of very good, unpopular algorithms that can be used in practice but are not well taught in schools or not well known. The first episode and this episode will be devoted to the Quinn Fernandez algorithm from 1991. It's a spectral estimation algorithm. What is spectral estimation? It's the estimation of frequency. Spectral estimation is actually a very critical and very well studied aspect of signal processing, with many applications in signal processing and across many scientific disciplines. In my field, the radar field, there's a lot of need to estimate frequency all the time, from range estimation to Doppler estimation to direction of arrival estimation. We are estimating frequencies all the time. Now, in specific applications that I work on and I research is vital signs, which is basically respiration and heart rate, are also falls under the category of spectral estimation or estimation of frequencies. As you probably know, the most common used algorithm is the Fourier transform or the fast Fourier transform, Fourier analysis, basically. We'll see that, and you probably know that it suffers from a lot of drawbacks, such as very demanding time windowing for resolution to very inaccurate type of estimation. Super resolution algorithms are also used quite a lot, like components, MVDR, music, and ARMA. ARMA is the autoregressive moving average algorithms or modeling. We will discuss an iterative ARMA technique presented first in 1991 by Quinn and Fernandez. So that's the paper. The paper title is a fast, efficient technique for estimation of frequency, and the actual reference citation is in the last page of this presentation. This is a beautiful paper. It's very, very fun to read, and I love the mathematics back of it. So let's talk about the model. The model is this is the model. Y of t equals a cosine and so on plus x of t, where x of t is a zero mean finite variance stationary process. Omega is the frequency that we want to estimate, and it's right between 0 and pi. And we know that a sinusoid is a solution for a second order difference equations. So the y of t also satisfies this equation, which is a second order difference equation. You can see that it's an unstable IIR. It does not have an invertible solution. The algorithm will be based on fitting an ARMA 2-2 model iteratively in a special manner. So the idea behind it is replace the 2 times cosine of omega with alpha and beta, and estimate alpha and beta under the constraint alpha equals beta. An iterative solver will fix alpha and then solve for beta and repeat with the new alpha until some sort of a stopping criterion is met. If alpha is known, a solution for beta is obtained by linear regression or the least squares algorithm, as detailed in the next slide. Let's dive into the algorithm itself. So the algorithm outline. Let's initialize. So one is the first iteration. Let's initialize alpha, denoted alpha 1 as 2 cosine of omega 1 estimated, which is basically an initial guess for the frequency. And now we run in a loop, in a for loop, iterating on j, and we define a new variable zeta to be this term, and this recursive term, and for t's that are less than 0, we instantiate zeta equals 0. Now we estimate beta j using the linear regression for this iteration. So it's alpha j plus a linear regression type of addition. And we continue iterating like that until bj minus alpha j is sufficiently small. If it is, we put omega as the r cosine of beta j over 2, and we break the loop. Otherwise, we continue iterating by instantiating alpha equals beta and doing it all over again. Very simple algorithm, and as we will see, very, very nice and efficient. So let's evaluate this algorithm on a toy problem. We did a Monte Carlo simulation in code. We compared it against FFT-based frequency estimation. We derived the Craméro lower bound, the CRB, and we compare the results against the CRB for the case of 0 dB SNR. That's how the sinusoid looks like when adding noise to get us to 0 dB SNR. And that's the results. So here we can see the vertical axis is the mean squared error in hertz squared. The horizontal axis is the number of samples. And we can see here the blue line is the Quinn and Fernandez algorithm. The red line is the FFT based. And the dotted black line is the Craméro lower bound. And we see that FFT stagnates or plateaus after a while. And the MSE, the mean squared error of the QF algorithm, tends to the bound when n increases. Basically, when number of samples increases, basically render the algorithm asymptotically efficient, which is very good. And we can see here also that in low sample sizes, we can observe that the FFT lacks in performance. That's the paper. The paper is from 1991. And that's, if you want to contact me for further questions, you can email me at this email, near@aleph0.ai. That's the first of few sessions of very short episodes that I will present very cool and forgotten algorithms for various applications, this time frequency estimation. And thank you very much for listening. I hope this added value to your arsenal in terms of algorithm design. And I personally can't wait to take this to a real radar application, real radar problem, and try this algorithm. Thank you.